Okay, hi folks. This is problem number 2 on homework number 3, and it shows you an I-beam with the dimensions given, which is clamped at one end. Its surface on the back is clamped at one end, and then this is allowed to sag under its own weight. Now, obviously, you need to know what the density is. Okay, so I'm not going to change the material properties here because this laptop that I'm taping stuff on it crashes when I try to change material properties, but you know how to do that. Let me go ahead and make this problem. This problem is probably more appropriately modeled with beam elements. The only issue with the beam elements in Catia is that, first of all, we haven't discussed it at this point in the course. But even when we discuss it, unfortunately, you won't be able to plot the stresses uh, for beam elements. Okay, some software allow you to do that, uh, but not in Catia. Okay, so let me go ahead and start with the part file. I'll go to new or part. So, okay, immediately I save this thing, file, save management, save as in that same folder, homework 3. I'll call this thing problem number 2. Okay. All right, on a convenient plane, on that vertical plane, I will sketch that I section. I'll do it in a very quick way and then clean it up. Okay, so where's the sketch profile right there? So different ways of doing it. For example, let me draw something and then mirror it. How about that? I'll do it like that. Yeah, something like this. There are other ways of doing it. As long as you get that geometry, it really doesn't matter. Okay, so clean it up. Look at the dimensions that we've got. So this is 0.5. Now, if I make this thing zero point 0.5, you're going to be upset because look at what happens. 0.5, right? But that's okay because that's because of the way I did this thing. So let me try it again. 0.5, 0.5, and you're going to panic. Okay, so let me move this thing here. There. Does that make you happier? All right, that's because some of these dimensions, like let me see for a second. Yeah, this should be yeah, this should be 0.25. Cancel that. 0.25, 0.25. Okay, the height, this dimension should be 1. From here to here should be 1. Okay, and this dimension is a terrible, terrible way of doing it, but that's okay. 0.25. There we are, and this should be 0.25. I think it's going to look a lot better. There, there's your I-beam. I don't know. Okay, good. So let me mirror these things. Let me select all of these. I'm done with this. Do control set. I think I missed something here. This was what was that? 0.25. Yeah. Somehow I did undid these things. 0.25. Okay, and this one is also 0.25. Okay, good. All right. So let me select these things. This control that, or you can trap it with the cursor. Trap these lines with cursor, and then you say mirror. Look for mirror right there. See that mirror? Mirror with respect to this line. Good. You can do it any other way that you want. Exit, and then pad it 10 inches, I believe, there. Now, we're not assessing accuracy in these problems. That's why, because probably the stuff that we're going to get as far as stress distribution around these edges is going to be totally nonsense, okay? Because you have to use a fine mesh in order to resolve that stress distribution. But, and in fact, the fine mesh relatively everywhere, close to these discontinuities, but I'm not going to do that, okay? So let me apply material properties of steel metal, because whatever I'm giving you in that handout is close to steel. There we are. Now we're going to save this thing. I think I already saved it. Yep. Uh, you switch workbenches, generative structure analysis. All right. Now this is a gigantic, gigantic, element. So double click on it. I'm going to use, I don't know, maybe, what does it say, zero point 0.6? I'm going to use 0.1. Well, at least, at least we're gonna kill the kill the fly with a cannon, so that's okay. Right click, mesh visualization. It's gonna be a lot of unnecessary elements, but hey, it's free. We're not paying for it. Okay. But if you're working for a company, these things actually have implications. Big elements, fast, cheap, inaccurate. Small elements, slow, more accurate. But making elements small everywhere does not make sense. So you have to look at areas where there are issues that you have to refine the mesh. But here we just did everything small. Now, you know what? Because this is too small, I'm going to change that thing from parabolic to linear. You don't see any difference, the same thing. Now, uh, this, let's sag actually, let's clamp the end, one end. This is the entire face is clamped, does not move in any direction. Now, and this is sagging under its own weight. Now notice that there is a plane of symmetry. Because of the nature of the problem, geometry and the loading and the restraint, there is a plane of symmetry. I don't have to do this. I can use only half of the model. And on a test, I will ask you to choose all planes of symmetry. If that is the case, you should cut this thing with the YZ plane, like this, along that line, and make sure that that cutting surface that you have created is on a surface slider. That's what plane of symmetry means. You can't just cut the geometry. You have to make sure you put rollers or surface slider on that cut plane. But I'm not going to do that. Now, the question is, how do we tell Catia that this is weight sagging under its own weight? Because I don't know, I don't want to calculate the weight of this thing beside. Even if I did it, where would I put it? So basically, this is like applying acceleration. It's just like weight is nothing, G is nothing but gravity, acceleration due to gravity. So if you look at these icons, we have used pressure, we have used force. This one looks suspiciously like a globe with a arrow, downward arrow, like gravity. And there are two actually options there. One is called rotational acceleration. We'll do that in the next week. And this is a linear acceleration. If you click on it, it says, okay, what is the support? Now, it doesn't matter what you pick, it picks the whole thing, okay, because it's a body force. So even if I selected this corner point, the whole thing is selected. And then it says, okay, what is your direction where the acceleration is applied? So obviously it's Z. Now the unit is, meter per second squared. So if I wanted to apply 9.81, I can do that, negative 9.81. So I can do negative 9.81, assuming this is on Earth. Or I can put, for example, 386 minus 32 point, I can put 32.2 feet per second squared if I wanted to. But also 386, negative 386 for gravity, the conversion is inch per second squared. or you can go actually change your units as you wish. 386 in the tools options dialog box. So if I click OK, or if I click on any of these things, it will convert this into uh, zero, it converts it to meter per second square. And I bet if I did that, it's going to become very close to minus 9.8. Yeah, you see that? 9.8. And then say OK. So we apply weight as gravity or as an acceleration. And this, for example, if this was the antenna on your car, it was mounted vertically on your car, and the car would accelerate, for example, with some direction along a highway, whatever the acceleration is, this will bend because of car acceleration on a highway, and it will bend by applying acceleration in the proper direction, maybe X or Y, depending on what the direction of the travel of the car is, and that'll give you the deflection and stress distribution. So let me save this thing. File, save management. Oops, where's that? File, save management, save analysis, save as in that same folder, except that this is going to be problem 2, homework 3. Yeah, problem 2. I don't know why I called it problem. Backspace. It's not enough light here. I can't see what I'm doing. And then say okay. Good. So let's run it on the compute. Remember, I'm using linear elements, so if you do parabolic, because this is a fine mesh, it may take a little bit longer. Deflection, down. Animate, there we are. By the way, notice that you can tell more deflection. I want more deflection. For example, if I put another 0 here, change the scale to be another 0 here, it's going to look awful. There. Oh, it's not too bad, actually. One more 0. Okay. Basically, you increase the scale of deflection. When you should always try to use default, because default is usually the optimum one for visual purposes. Now, deflection, click on the displacement. These are the number, very small. Remember, this is a thick piece of steel which is deflecting under its own weight. It's only 10 inches long. Maybe if this was a 10 feet long, the deflection would be more, but this is just, 10 inches long and very little stress and a very little deflection. If you look at the von Mises stress, it'll show it to you. Needless to say, the biggest stress is going to be at the wall, because bending moment is maximum at the wall. But uh, it could be that the stresses along these edges are also high, but not in this problem. Let me show you something. If I probably went and look at the, let me make a group here. Okay, to move it, so let me click on this active box, grab this thing, put it where I want. Okay, so let's say all right. I'm going to hide the box. Double click on this either on the contour here or from the tree. Here it is. If you double click here, basically it's like double clicking on this edge, and select the selections tab, and I want the box. You see, you could not see these because you were too close to the end, and uh, those big stresses at the wall would mask anything else. But anyway, that shows the stress distribution for the I-beam. It's not a it's not a secret that the top and the bottom bending stresses are maximum there. But of course, you have to be also careful about these edges where discontinuities may arise. Not quite discontinuity, means rapid changes in stress concentrations, basically. If you're done, you just double click on it, and if you want to see everything back, just click on the arrow to show you everything. That's pretty much it. Good luck.